Okay, so today we're going to look at some applications of the centroid, namely finding surface areas and volumes of surfaces of revolution. So similar to what you may have done in Calculus 1, you have some line, rotate that around some axis, and you get either some surface area or volume out of that shape. Similar thing here, but instead of having to integrate, we can just use the centroid. So that's the theorems of Pappus and Gildenus that we're going to see. Then we're also going to see some general distributed loads. So everything we've done so far with the centroid has been two-dimensional distributed loadings. Today we're going to get into three-dimensional distributed loadings. So theorems of Pappus and Gildenus, like I said, I can have a line or some area, rotate that around an axis, and that's going to give me some surface area and or volume. And I can find the volume and or surface area, as I said, using the centroid and these two theorems. And so one thing that I have to have is that this curve that I'm rotating around cannot cross the axis. If it crosses the axis, that doesn't work. So as long as it stays on one side of the axis, rotate it around, I can then find either surface area or volume. So first one is surface area. So again, I take this line like I did here, rotate it 360 degrees all the way around my axis, horizontal line here, and I get this cone-shaped object, and I can find the surface area of that cone-shaped object by simply taking the angle through which I rotate it. So in this case, it would be 2 pi. So again, this angle has to be in radians. So 360 degrees, 2 pi, all the way around the circle. R bar being the centroid, so wherever the centroid is located perpendicularly from the axis, and then multiply that by the length of this line, and those three guys multiplied together simply gives me the area. So like I said, no integration involved once I know the centroid. And of course, this doesn't have to be rotated all the way around 2 pi. It can be rotated around any number of degrees, but again, as long as that angle is in radians, just multiply those three things together, and that gives you the outer surface area of that shape. And so if I have a half circle, rotate that around, it's going to give me a sphere. If I have a straight line that intersects the axis, that's going to give me a cone. If I have a circle off the axis, rotate that around, it's going to give me a donut shape, which is called the torus. And again, I can find the surface areas of those by just finding the centroids of these lines and then multiplying it by the length of the lines and whatever angle I rotate it through in radians. Similarly for volume, in this case, I'm not looking at the line, I'm looking more at the area. So instead of just having that line here, I want the entire area that I'm rotating through that angle. So I have, again, this area here. Underneath that line, essentially, that whole area gets rotated, and then that's what gives me this volume that's shown in kind of green. A very similar equation. To get that volume, I take whatever angle I rotate it through, again in radians, multiply that by the centroid. In this case, it's the centroid of the area. So slight difference here. They're both called R bar, but in this case, I'm looking at the centroid of this area. So this R bar corresponds to that area, or this area here, as opposed to the previous case when I dealt with surface area, this centroid correspond to this line. So this is the perpendicular value of the centroid for just this line, not the area. So be sure to get those right when you're doing this, because there is a difference. And so volume, again, very similarly, angle through which I rotate it, centroid of the area times the area itself, and that gives me the overall volume. So in this case, again, my sphere, I'm looking at the area inside the sphere, rotate that around gives me a solid sphere where I can find the volume. Same thing for the cone, same thing for my donut shaped torus. Again, in this case, I'm finding the volumes. That's why I have those shaded in. And so that's for one single shape. I can also do that for composite shapes. So there's kind of a couple ways you can either find the length of a line or an area. You can either find the length through some sort of integration, or same thing for the area. You can find the area under that curve through integration. Or maybe it's a situation where I can take that area and build it out of simple shapes like rectangles and triangles and semicircles, things like last class where we saw to find the centroid, I built some objects out of smaller objects. Same sort of thing here. I can do the same thing. Where to find the overall area, I take the angle through which I rotated, and then the centroid times the length of each individual line. Add all those up, and that gives me the total area. Or similarly, take the centroid of the area times the area of each individual little component. Add those all up, multiply by the angle through which they're rotated, and that gives me the overall volume. And then last thing for today is, again, this two-dimensional distributed loading. And so I have a distributed load in both the X and Y directions, pushing down in the Z direction essentially. And just like before, I want to take this distributed loading, has some loading functions, so it could vary in X and Y. So this should be different at different points. Define the total force pushing down. I need to know two things. I need to know the magnitude of this total force and where does it act. So I need the magnitude, Fr, as well as this location. So X bar and Y bar from the origin. Where do I actually place that total loading so that it produces the same translational and rotational effects as the original one? And so in this case, because it's a two-dimensional loading, I need to know location in terms of 2 dimensions, and that will offset both the total force pushing down as well as moments around the X and Y axes in this case. So this individual force Fr does the exact same thing as my original loading. And to get that is essentially the same as what we did before. So to get my magnitude, I just integrate my pressure distribution function, similarly to what we did for the one-dimensional case. Only difference now is that I'm integrating over 2 dimensions. So dA is generally just dx times dy. So 2 integrals, one in the x direction, one in the y direction. Integrate that surface area on top, whatever it is, and that essentially gives me a volume. So similarly to what happens in the two-dimensional case, I integrate under the line and I find the area under the curve. This case, because I'm integrating a two-dimensional line, an area essentially, when I integrate that, I get the volume under that top surface. And so this total force magnitude Fr is essentially the volume under my loading curve, or my loading sheet area, whatever you want to call it. And then in terms of where to put this, so now again, I need 2 equations, one for X bar and one for, because I need both X centroid and Y centroid essentially. And essentially that's what these integrals are, is finding the centroid. So I take X times my distributed loading function, integrate that over both dimensions, X and Y, and that gives me the X centroid value. You can see that is essentially just the volume, because that's what we found for P. Integral of PdA is just the volume. And so essentially my X bar is my X coordinate of this volume. Similarly, my Y bar, Y centroid, is just, again, Y centroid of this volume is where I want to put my force Fr. So line of action of my single concentrated force passes through the geometric center, the centroid of, again, this volume, whatever I make out of this two-dimensional general distributed loading function. So that, again, as usual, examples of those will be seen in class later today. So I'll see you all then.